So hello everybody, my name is Thom Badings. I'm a postdoc in the a.k.a. project. I started last November, and in this talk I will give you sort of an overview of a lot of the research I've been doing as part of my PhD, but also since I started my postdoc here in Oxford. And so today's talk is going to be about control of stochastic dynamical systems. And I'm going to focus on basically two directions that we took here. One is more abstraction-based approach, and the other one is what we call a certificate-based approach. And I will explain everything about what that means. Just also open the chat here. Perfect. So a little bit about myself. So I come from the Netherlands, where I started my studies here in the north at the University of Groningen. I did my studies in industrial engineering and management, after which I moved to a little bit more south of the Netherlands, where I did my PhD in computer science. And then last year I moved to Oxford, starting in the Oxford Control and Verification Group, together with working a lot with Alessandro Abate. And so in my research, I like to focus on sequential decision-making problems. Right, and one very typical example that I always like to show. I'm afraid the videos are a bit more chunky than I hoped, but is that of an autonomous drone delivery problem, right? So we want this drone to safely deliver a package from an initial position to a target, and of course, while doing this safely. This means that the drone must navigate around obstacles, reason about its environment, and so we get this kind of sequential decision-making problem that we want to solve. And so the main challenge here is, how can we guarantee that this drone behaves safely, even when it's deployed in challenging and uncertain environments? And so this kind of decision-making problems arise in many different domains, right? This includes things like autonomous drones that I showed, but also in maintenance planning or in power systems, in epidemic modeling, but also in self-driving vehicles and in robotics. But all of these problems in these different domains have quite a few different things in common, right? So generally speaking, that is as follows. We are given a model of the system that we study, and we have a certain specification for its requirements. Then, given these ingredients, we want to compute some sort of optimal solution, a plan or a strategy, or policy, we often also call it, together with a measure of how good this policy actually is, right? Maybe in the form of the probability that we are able to carry out the task that we have in mind. And so now a number of things make this kind of problem very challenging, right? So first of all, that is that these problems, as I mentioned, are sequential. That means that we have to carry out multiple tasks after each other, and the action that we take at every step might influence the things that we encounter later on. Second of all, these problems are safety critical, right? So this drone here, for example, needs to navigate around the obstacles while flying towards the target. And finally, we also have to deal with lots of different uncertainties, right? Because this drone needs to maybe fly through uncertain weather conditions, and we might also not know exactly the state of charge of the battery. And so we want to solve these decision-making problems under these different challenges. And that's going to be the main topic of the rest of this talk. And by the way, if at some point there are any questions, just let me know or post them in the chat. I'll try to monitor it on the side. So let's make this as interactive as possible, I would say. So going back to the title of this talk, how to control your stochastic system, a tale of abstraction and certificates. Well, if we want to make this a bit more concrete, let's say, then the title should actually be something like, okay, the verification and control of discrete time stochastic dynamical systems with temporal logic specifications using one of two approaches, right? As I mentioned, one thing that we're going to discuss is how to use abstraction-based techniques to solving these decision-making problems. And the other approach is that you can take a certificate-based approach, where we're also going to leverage some machine learning, some learning-based techniques to solve these verification problems. So let's make the problem set first a bit more concrete before diving into these two different types of directions. So what kind of models are we really working with? Well, we work with discrete time stochastic systems. And these are dynamical systems that evolve over discrete time steps, and they are stochastic. Right? So you can also just say it's a continuous state action Markov decision process, or MDP. So what do we have here? Let me actually use the pointer for this. So what do we have? Well, we have a continuous state that evolves over discrete time steps. We have a continuous action that we can choose in some way. And we have some stochastic noise term that evolves according to, it's a stochastic process that evolves according to some underlying probability measure, right? And so then the state at every step is updated as follows. We have a current state, a control input, and a value for stochastic noise, and it simply outputs the state at the next time step. Alternatively, you could also write this by not making the stochastic noise explicitly, but instead, as what you would commonly do when dealing with an MDP, is say that we don't have this W, but instead it maps to a distribution of states at the next step. Okay, then what we want to design is a policy or controller that chooses these control inputs, right? And the simplest thing that you can work with, and I'm going to just restrict it to that here, is to choose a memoryless policy which just observes the current state. So this should actually be X, the state space, and it outputs the action that is then taken given that state. Yeah. Now, on the other hand, we also need a way to represent the specifications that we consider. And there are lots of different temporal logics that you can use for this, right? LTL is very common to use for this. In control theory, lots of people also make use of what is called signal temporal logic. But in our work, we mostly focus on probabilistic computation tree logic, or PCTL, which is also, I would say, the most widely used logic for verification of Markov decision processes. And just for the sake of this talk, I'm going to restrict it even further, and we're going to just purely focus on reads while avoid specifications. So very intuitively, this means that we have a control task where from a given initial state, we want to reach a set of target states, while always until then avoiding some unsafe states, right? And if we are able to do this, then we satisfy the reads while avoid specification. And to denote the satisfaction of the specification, we use this satisfaction relation as shown here. Yeah. Okay, so what do we get then? Well, if we have such a discrete time stochastic system together with a reads while avoid specification, then this induces a stochastic process, right? So we start at some initial state, xi, which is the state at x0, time 0, and then at every next step, the state is sampled from the dynamics where this is the part where the stochasticity comes in, right? So we get this kind of closed loop system if we fix a control policy that induces this stochastic process over trajectories, and this is really the space in which we want to reason about the behavior of the system, right? Because now we can ask, okay, if we now have this specification in mind, what's the probability that our system generates a trajectory that satisfies the specification? Yeah. And this is really what we want to reason about. So first of all, we can ask a verification question, which essentially asks, okay, given a policy, verify whether the probability of satisfying it meets a given threshold, right? So really just decide, is the probability of satisfying the spec above this threshold of rho? Then, alternatively, what we can ask is for a synthesis problem, right? We can ask, okay, compute such a policy such that the probability of satisfying the specification meets this threshold. Yeah, And in my research, and also today, we're going to mostly focus actually on the second version, right? We're going to look at a problem where we want to compute both a policy and we want to verify that that it satisfies the specification with this threshold probability that we have in mind. Okay, and now this is where it sort of branches the story, because we can take different techniques for solving this problem, right? And I'm going to start with the abstraction-based approach, where from a very high level point of view, the idea is, okay, we have our continuous stochastic dynamical system, and solving this verification or synthesis problem on the stochastic system, the continuous system directly, is just infeasible, right? So what do? We create a simpler abstraction of this continuous system, and then use probabilistic model checking techniques on this finite-state abstraction to solve the problem. And then what we do in the end is that we sort of lift back the solution on the abstract domain back to the continuous one in such a way that we can solve this problem. So with a little bit more details, this means the following. Well, we have this stochastic process induced by a policy, right? If we would fix a policy on our discrete time stochastic system, then we get the stochastic process. And we want to design this policy such that the satisfaction probability meets this threshold of, well, here it's P star. Now we're doing this by constructing this abstraction. And the nice thing is that, okay, even though computing an optimal policy on the continuous domain directly is infeasible, what we can do is quite easily, with just standard model checking techniques, we can compute an optimal policy on this abstraction. And then if we construct this abstraction in a very clever way, let's say, then we can always, then by construction, we can always refine back the solution on the abstract domain back to the continuous model. Yeah. Now, we want abstraction to have a number of properties. First of all, it needs to be rigorous in the sense that it can be used to provide guarantees on the discrete time stochastic system. Second of all, we want it in some cases to be, well, say, data-driven, right? Because we want to construct these abstractions even in some cases when we do not have perfect knowledge of the dynamics of our system, right? And so how do we do this? This is a challenge. And finally, we want these techniques to be, well, relatively efficient. Where I roughly just mean, well, we want to be able to use it to solve relevant control problems in practice. And as we shall see, well, I would say the first two bullets we can pretty much satisfy, right? This is really doable. The third one is kind of questionable, I would say. I mean, these abstraction techniques, as I will explain later, they're just very expensive in lots of cases to use, right? And of course, you can use smart techniques to try to overcome these limitations. But abstraction just kind of has this notorious a consequence of being computationally expensive. But anyways, let's go a bit more into it. And I'll try to just give a sort of intuitive explanation of how we construct such an abstraction. So, as I already mentioned, we want to construct an abstraction in the form of a Markov decision process, an MDP. Just for the sake of completeness, I also copied the MDP definition here on the slide. So for those of you that are very much familiar with these definitions, I'm sorry. But an MDP is basically defined as follows. We have a finite set of states. We have a finite set of actions. We define some sort of initial state of the model, and we have a transition probability function, right? So the MDP is just sort of the finite state counterpart of the discrete time stochastic system we started from. And so what do we do to generate this abstraction is the following. The first step is to partition the continuous state space into regions, right? So for computational reasons, we typically use complex polytopes, right? Because then you can very cheaply just determine, okay, if I have a continuous state, does one of the regions contain that state or not, right? With polytopes, that's very cheap to do. And then simply we say, okay, every of those complex polytopes represents one of the states of our MDP. Yeah. Then the second step is to define somehow, okay, what are these actions of the MDP? Yeah. And I'll explain this on the next slide. third, we then need to compute, okay, if we now have these states and these actions, what are the transition probabilities in this abstraction? And finally, we need to compute a policy on this abstract model that in the end we can then carry back to the continuous domain to solve the problem that we really care about. Okay, so how do we do this? How do we define these actions? Well, I would say there are basically two ways in which you can do this. The simplest way that you can do it is simply to say, okay, I have this continuous set of control inputs that my dynamical system can take, and I'm simply going to discretize it, right? And every MDP action is then associated with one of these discretized inputs. And this means basically the following from a pictorial perspective. So suppose that, okay, we have our state space, and suppose that this box is one of the polytopes of our partition. Then we essentially say, okay, within this box, this box represents one abstract state, and within it, in all the continuous states in that box, we're gonna execute the same continuous control input if we choose a certain abstract action, right? And this is very straightforward to do, but as you can imagine, well, this leads to approximation errors, right? Because, well, if I choose a particular action here, then I obtain a distribution over states over here. Well, if I start from a different state, well, then I get to a distribution over states that's maybe located here. So essentially what this causes is that we get diverging distributions over successive states, right? And this means that we would get a very conservative abstraction that is only a loose over approximation of the original dynamics. But luckily, we can do this in a little bit more smart way, at least in a lot of cases. And that's the following. So we're not going to discretize the continuous control inputs yet, but instead we're going to say the following. We're going to say that executing a certain abstract action is associated with executing a control input that still depends on the precise continuous state where we are. So again, pictorially, this means that, well, now depending on which state I'm precisely at, I can actually say, well, I take a different continuous input corresponding with a certain abstract action, right? And the advantage of doing this is that we get distributions over successive states, which are ideally at least way more close together, right? And even in the most beneficial case, we sometimes can even make it such that the outcome of an abstract action is actually independent of the precise continuous state where we choose it from. Yeah. Okay. Now, what we then need to do still is define the transition probabilities of this abstraction. And I'll also be just very high level here, not get into too much details. But the basic idea is just that we now have, okay, if we choose a particular abstract action in a certain state, then we get some sort of distribution over successive states, right? So this ellipse, by the way, it sort of assumes that, okay, if I have some stochastic noise in my dynamical system, which is Gaussian, then yeah, like the level sets of this distribution over successive states, it's an ellipse, right? So this ellipse just visualizes this distribution over successive states in that way. And so now the idea is basically just, okay, we want to know what is the probability that we say end up in this particular successive state, right? And that probability we simply just get by integrating that distribution over successive states over each of the partition elements, right? And that might be computationally expensive because we have lots of these discrete states in some cases. But if the noise distributions are pretty straightforward, then at least we can just do this, right? If the noise is indeed Gaussian, maybe even with diagonal covariance matrix, and it's additive, then this is pretty straightforward to compute. But on the other hand, there also might be cases where, well, we don't know these noise distributions precisely, or maybe these distributions are actually unknown at all, right? So what do we do in those cases? Well, what we do is instead we take a sample-based approach to this problem, right? So what do we say? Is rather than having this distribution over successive states, we observe samples from this distribution, right?
And then we want to know, okay, we have this distribution over successive states. We took a bunch of samples from it. And based on these samples, okay, what's the probability that my next sample would be in, say, this discrete state? Right? So what this boils down to is essentially bounding the success probability of a binomial distribution, right? Or even of a Bernoulli random variable even. So what we can do in practice is observe the number of samples that we counted in each of these successive state regions. And we use this to obtain an upper and a lower bound on the transition probabilities of the MDP. Yeah. And so what does this mean in practice? Is that we get an abstraction which is represented in the form of what we call an interval MDP, right? And this is nothing else than a regular MDP, but then with intervals of transition probabilities, right? So, by the way, this example interval MDP, it doesn't resemble anything on the left. It's just to show what it could look like in interval MDP. But the main thing is here just that, okay, if I take a certain action, then I still have a interval of transition probabilities to the next state, right? So essentially what you can interpret this as is that an interval MDP defines some sort of stochastic game where the agent picks the action and then some adversary chooses these transition probabilities within the intervals, right? And this allows essentially for robust reasoning in this interval MDP. And this is precisely what we're doing to solve this synthesis problem on the abstraction. Okay, so putting it all together, the kind of setup that we obtain is as follows. So we have an algorithm that essentially says, okay, we're gonna construct an interval MDP abstraction, and we're then computing an optimal policy on this abstraction, right? The abstraction is just finite, so it's straightforward to do this computation. We can use off-the-shelf probabilistic model checking techniques to do this. And then we have a theorem that essentially says the following. Okay, for every policy on this abstract model, there exists a policy for the concrete system for which the satisfaction probability is at least as high. And now I'm neglecting something, namely the phrase of, okay, with probability at least beta. And this is caused by the fact that we use a sample-based approach to generate this abstraction, right? Because we use these samples, we can always have bad luck with these samples, right? So there's always a small probability, which we can quantify, but there's always this probability that the abstraction that we get is actually incorrect, right? And so this confidence probability here accounts for that fact. But anyways, we have this result, which essentially says, okay, if we compute anything on the abstraction, then we can translate it into a policy that performs at least as good as it on the continuous system, right? So what can we do with this? Well, okay, if we have an optimal policy on the interval MDP and say that the satisfaction probability is 95%, right? Well, maybe actually we wanted the policy a threshold of 98%. Well, that means it's not good enough, the current results. And what we can do is try to go back and improve the abstraction, right? And if at some point we find a policy on the abstraction which is good enough, then we use it to compute one for the continuous system. And then we have found a solution to the problem that we started with. Yeah. Okay, so we have implemented all of this and performed experiments in a number of different papers, numerical experiments, and I just want to highlight two of these here. So what you see here is on the left two figures, a drone motion planning problem in sort of a windy environment, right? So these drones, they need to fly through the windy environment while not crashing into the red boxes and reaching this green target. And it essentially is a six-dimensional stochastic dynamical system beneath this, and we generate an abstraction in the form of this kind of interval MDP, and we're able to use that interval MDP to compute, well, essentially provably correct control policies for this system. Yeah, and so the interesting thing also is that if there's a lot of wind, if there's like really high degree of noise, then also under this policy, the drones, they fly around this obstacle and take the longer route to the goal. But on the other hand, if there is pretty weak turbulence, then these drones actually take the direct route towards the goal, because it's still safe to do, right? And it's faster, so then in the end, it's still better to do. So this, I think, pretty nice to see that this difference in noise value actually really also affects the policy that you get in practice. Now, the experiment on the right was for a satellite rendezvous problem, where, if I'm not mistaken, the white satellite starting here, it needs to reach the green one while not crashing into the red one, right? And so the kind of benchmark, the kind of problem we're solving is virtually the same as for the drone planning problem, and just on different benchmark, showing that we can still solve these kind of problems in practice. Okay, so then to conclude the first part of the talk. So are abstractions now any good in practice? You can ask. Well, on a positive side, it's very nice that these kind of abstractions, they can handle very general things, right? They can be stochastic, nonlinear, and also they can be partially unknown or even fully unknown, in which case you would need to use a data-driven abstraction technique, which we also have worked on in different work. So that's pretty nice. Well, also what's nice is that we can use it to compute provably correct policies against complex temporal logic specifications, right? So this goes beyond a lot of the standard techniques in control, which mostly focus on simpler objectives of maybe stability or invariance, right? And this really goes beyond this by combining it in temporal logic specifications. Now, it's not all good, because these abstractions, they can also be very expensive to compute, right? And one notorious problem here is, well, essentially the curse of dimensionality, saying that the number of states in this abstraction really is exponential the number of variables, right? So it really explodes pretty quickly once we go to systems with higher dimensions. Now, what does this mean for the challenges that remain, I believe? Well, first of all, it's actually also a challenge, I believe, to make good tooling available, to make these kind of techniques also accessible, right? Because in lots of cases, in papers, these methods, and also like we do, they are implemented in prototypical tools, but I would not really call these tools very accessible, right? And I think that by making a connection, by developing such a tool, we can also make these kind of techniques much more applicable in practice. And also one other quite interesting idea for further research, I believe, is to make interesting connections between abstraction-based techniques with machine learning, right? Because what can we do maybe is the following. Okay, if we can use a very naive, off-the-shelf learning algorithm to find an initial, but maybe decent policy, then we can restrict the search space in this abstraction by a lot by only focusing on the relevant portions of the state space, right? So we can combine learning and abstraction, I believe, in smart ways to make these approaches scale much nicer in practice. All right, so that basically concludes part one of the talk. And I would say let's just maybe wait with questions till the end. Because I also want to talk now a bit about this second direction, which is about using certificates to solve these synthesis problems. And so let me start from, again, a high-level perspective of what we're going to do. So the idea is that we want to find a mathematical function that maps from system states to real values, and we want that this function essentially proves the satisfaction of the specification, right? So this might sound familiar to some of you, because in lots of contexts, people have used these kind of functions a lot, right? In control theory, there are Lyapunov functions, there are barrier functions, and more in computer science, in program analysis, people make a lot of use of ranking functions. And also one particular category of these certificates is presented by supermartingales. And supermartingales are also the kind of functions we're going to use today as a certificate for these kind of reads while avoid specifications in stochastic systems. And so the high-level plan is going to be the following. Well, we want to learn such a certificate that proves the satisfaction of the specification. And in particular, what we're going to do is that we're going to represent the certificate and also policy as a feed-forward neural network with ReLU activation functions in this case. That just simplifies our life a lot in this case. But we're gonna do that. And then what we want is that we are going to train this certificate together with the policy in a typical counterexample guided manner, right? So what we essentially have is that we have a learner module that's going to train the certificate and the policy in such a way that it hopefully is a correct certificate. And then we have a verifier that tries to prove the validity of the certificate, right? And so either the verifier succeeds, in which case we have a formal proof that the reads avoid specification is satisfied, or the verifier returns counterexamples, and the learner uses these counterexamples to try to further improve the certificate. Yeah. Okay. So moving a few steps back, actually, just to provide some sort of intuition of how these kind of certificate functions work. So the simplest kind of certificate, and the most classical one maybe, is a Lyapunov function, right? So what does a Lyapunov function do? It proves stability or even asymptotic stability in nonlinear control systems, right? And so the basic idea is as follows. A Lyapunov function is a function from system states to non-negative real values, right? And this function is 0 in the origin, and it's strictly non-zero everywhere else, right? And then we also have the condition that along system trajectories, this function needs to decrease strictly in value, right? And okay, what does this mean essentially is that we have this kind of cone shape where the function has a value of 0 at the origin and is non-zero everywhere else, right? But we require that along system trajectories, we need to decrease in value, right? So the only thing that can happen is that ultimately then we end up in the origin, right? And therefore, this proves that the system is asymptotically stable, right? No matter where we start from, the system always converges to the origin, right? And this is just a very classical way in control to prove whether a system, a nonlinear system, is asymptotically stable. And so what we're now doing this is essentially the exact same thing, but now for richer specifications, right? So we're doing this for reads avoid specifications. And the idea is now that we're gonna find a certificate, which is some form of supermartingale, right? So a supermartingale is a stochastic process which decreases in expectation in every step. And the way that we're using it is as follows. So we want to find a function which we call a reads avoid supermartingale, which is again a function from system states to non-negative real values that satisfies 3 properties. First of all, we want that in all of the initial states of our specification, the value is at most 1. In all of the unsafe states, the value needs to be at least this value of 1 divided by 1 minus rho, where rho was the satisfaction probability, this threshold, right? And what we have is a expected decrease condition, right? So what we impose is that at every step along our system dynamics, the value of the certificate must decrease in expectation, right? And we even require it to strictly decrease by some minimum epsilon, because this really is needed to prove in the end the satisfaction of the specification by means of this certificate, right? So pictorially, this means the following. We have this maximum value in the initial states, we have the minimum value in the unsafe states, and we need to decrease along trajectories, right? So what we can then prove is that the probability of actually hitting the unsafe states is very low, right? And at the same time, reaching the goal, because we decrease in expectation, we will eventually get there as well. Okay, so now we're not the first ones to use these kind of certificates. Others have done this as well. But one key problem is that actually verifying the validity of this kind of certificate is very difficult in practice, right? So there are two main reasons for this. First of all, it requires reasoning over expectations of nonlinear dynamics, right? And we need to check this in a continuous state space. And also what makes it much more difficult is the involvement of neural networks, right? Because what do we need to do now essentially is that we need to compute an expectation over a neural network, right? And as far as I'm aware of, at least, all work on this still is either very computationally expensive or requires on loose over or under approximations of these problems. And so what do existing approaches do is the following. Well, there are a number of different things that you can do. Well, one thing is that you can encode it as a SMT query, right? And then you can use SMT solving to solve this kind of problem. Another thing that you can do is you can try to over and under approximate the dynamics and then use some sort of branch and bound scheme or mixed integer linear programming. But what we're using in our research, in our recent paper, is that we're using discretization of the state space and then using that together with the Lipschitz continuity of the dynamics and the neural networks. And so let me try to just intuitively explain what I mean by this. So the key idea is that we're going to verify the validity of the certificate by checking stronger conditions on the discretization of the state space, right? And then we're going to use Lipschitz continuity to generalize to the entire state space. So essentially, this means the following. If we have our state space with initial states, some unsafe states, and the target states, then we're discretizing it. Oh, sorry. This is the condition that we need to satisfy, right? This is what we want to show. And we're going to do that by discretizing the state space, right? So this means that we now have cells of a certain width. Let's call that tau. And what we're doing is we're checking a stronger condition on the discretized points only, right? And if we then make this condition stronger by tau multiplied by the overall Lipschitz constant, then satisfaction of this term here implies that the expected decreased condition is satisfied everywhere, right? And so this is essentially what we do. There's one more difficult thing, is that we also need to compute this expectation here. What we do is essentially a very naive thing where you can over approximate this expectation by means of a finite sum obtained by discretizing the noise space. Yeah, but in the end, still it leads to a sound, or at least a sufficient condition for satisfying this expected decrease condition. Okay, I think I'm just gonna skip this slide pretty much, but we can do this a little bit more tight, right? Because we don't always have to use Lipschitz continuity, but instead there are also ways of essentially passing boxes through neural networks. And in some cases for us, that leads to slightly better ways of verifying these conditions, right? But for the expected decrease condition, we cannot really get around this, and we still have to reason about this expectation, and therefore use also the Lipschitz constant. And so this brings me essentially to, well, in a nutshell, also the two main challenges and therefore also contributions that we make in this paper. And that is, okay, we can verify these certificates in this way, but it's very computationally expensive, right? Because if we require a very high threshold probability with maybe these 6 nines, then we need a super fine-grained discretization of the state space, right? And also what it means is that training of the neural networks becomes less stable. And that is why we make two contributions in our work, is that first of all, we're proposing slightly different conditions for the certificate itself. And second of all, we're computing tighter upper bounds on Lipschitz constants for neural networks. Given the time, I'm going to be pretty high level from this point on. So I'm going to skip maybe some of the details that are on the slide, but feel free to ask afterwards. So the first contribution that we make is that we actually want to make this safety condition a little bit nicer, right? Because as I said, if we plug in a value of rho super close to 1, then this grows to a very high value. And this is not nice for the Lipschitz constant and also for training the neural network. What we do is actually very simple. We take the logarithm of all of these conditions, which leads especially to a way nicer safety condition over here. Right? So this grows way less with the value of rho. And that means smaller Lipschitz constants, and therefore also it leads to more stable training. Then the other contribution that we make in terms of computing better upper bounds for Lipschitz constants of neural networks is the following. So existing methods for this are either very expensive or yield very loose upper bounds on Lipschitz constants, right? And so the most straightforward method to compute the Lipschitz constants for a feed-forward neural network is basically the following. Well, we had these radio activation functions, and the Lipschitz constant of that is just 1. So we just neglect it. And what you can then just do is take every linear layer of the neural network and just multiply the Lipschitz constant of every layer together, right? So this is very cheap and easy to do, but at the same time, it also is very loose. It's just very conservative. And so what we do instead of this is that we make use of weighted norm systems to compute a little bit at least smarter Lipschitz constants. And so intuitively, what this allows for is to account differently for changes in the function in different directions, right? So if we do this with the standard way, then you always get these kind of square boxes for which you get a result. But with weighted norms, you are essentially allowed to stretch these boxes in one direction or the other, right? And that in practice is just very, very beneficial for us. So I'm going to skip some of the details of this example, but pictorially, the outcome is as follows. So say that we have a neural network and we want to evaluate, okay, what inputs lead to a value between -1 and 1. Then if we go back one layer and we use a standard method for computing this Lipschitz constant, then we get this red box, right? With the weighted norm, we can already improve this towards this box. And so bigger is better, right? Because this says, okay, if we start anywhere in this set, we are guaranteed to end up in the interval of -1 to 1. Now it becomes even nicer if we have multiple layers, right? Because this benefit grows actually with each layer of the network. And so in the end, we can guarantee this with the black box, while if you take the naive approach, then you would end up with this red one, right? And so this really shows that we can obtain tighter upper bounds on these Lipschitz constants in practice. Okay, just very quickly, we implement all of this in this learner verifier framework, and overall this leads to a sound but not complete algorithm for constructor synthesis, right? If the verifier concludes, hey, the certificate is correct, then we have a formal proof. If it's not able to do that, then we know nothing, right? So in that sense, it sounds but not complete. And the loss function that we're using essentially just represents a differentiable version of the conditions that we have on the certificate. Yeah. Okay, then just some experimental results that we got are the following. Oh, it's a bit visible by the choppy animations. But what you see here is the certificate being trained over the iterations of the learner verifier framework, right? And so what you see in the middle are essentially the remaining counterexamples in every iteration. And you see that at the start, there are quite a lot of these counterexamples, but over the iterations, these counterexamples are mitigated until at some point there are none. And that means that we have successfully verified that that the certificate was correct. Yeah. We also did this on a number of other benchmarks. And the nice thing is that especially due to these logarithmic conditions, we can verify reads avoid probabilities with super high threshold probabilities. Of course, if we would push this exactly to 1, then everything would break, because still the required value would grow to infinity. But at least with the logarithmic conditions, we can get this super close to 1. And that was not possible with the original conditions from previous work. Okay, So to also conclude the second part, well, are certificates any good? Well, again, actually, it's pretty much similar. As for the abstractions, they can handle stochastic, nonlinear, and partially unknown dynamics. In some cases, although that is actually very challenging still. And we can provide these provably correct controllers for complex specifications. Now, what is more difficult with these kind of abstractions is actually the following. Well, a certificate only holds for a fixed specification, right? So in abstraction, what we could do is, okay, first build the abstraction, and only in the model checking say, okay, now we care about this particular specification. For a certificate, that's different, right? Because the conditions for the certificate are inherent to the specification that we have in mind. So it's more tailored towards it. And again, actually, a joint negative part is that also these certificates, they don't really scale nicely in practice, right? So with this discretization-based approach, it's still exponential in the number of variables that we have. And that's just not nice for scalability. So what are the remaining challenges? At least two of those. First of all, I think we should be looking into ways of avoiding the discretization altogether, right? And one promising approach for this might seem to be SMT solving, but the problem is that SMT also doesn't scale nicely for this, right? Because SMT solving for neural networks is not really nice. We also have this expectation over the stochastic dynamics, which does not play very nicely in SMT. And there are other issues with this. And second of all, what I'm also super interested in at this moment, at least, is to try to generalize these kind of certificates to models whose dynamics are uncertain or maybe even completely unknown at all. And therefore, we need to combine this with sort of data-driven approaches to also in some way learn the dynamics at the same time. So that basically concludes my talk. Thanks everybody for listening, and I'm happy to take any questions right now.